Engineering. This is CIVL202 Statics, looking at Learning Objective 6, Moment of Inertia. We're expanding on our discussion of this previously to look at the Parallel Axis Theorem and the Composite Body Theory that will allow us to calculate moment of inertias for common shapes far more easily than double integration. Just as a reminder, this is statics, and so everything we're doing here is going to be critically important to what you're doing in the future. Your mechanics and materials professors, your statics and concrete professors, even your manufacturing machines and composite professors are going to expect that you know how to use the composite body theory to calculate a moment of inertia for a common shape. This is one of those other topics, and so with that, let's jump straight into it. So the thing for us to keep in mind here is that the parallel axis theorem is actually discussed in your textbook in section 10.2. It's all about calculating a moment of inertia about an arbitrary x-axis. So let's say we have some body out here, some shape, okay? And we're going to have an arbitrary x-axis running through it, something like this, okay? And so we want to find the moment of inertia, so the integral of y squared dA as we integrate for it to give us a feel of how it's acting around that x-axis. Well, the way we can do this using the parallel axis theorem is that we can first find the value of the moment of inertia xc, so that's about the centroidal axis. So if we were to take this shape and using what we know from earlier in the semester, we were able to find the centroid, we could find an axis parallel to x, but that passes through the centroid, something like that. And we could find the moment of inertia for that. It turns out that this moment of inertia is going to be the smallest moment of inertia for any given body, and conveniently for many common shapes, it's tabulated in our FE reference handbook in the back. And so we can go and pull this value from a table more often than not for our shapes. Then what we're going to do is we're going to add, see, we've increased the distance, right? We've moved it away from the axis. So we've got some distance here, dy, that we need to account for. And so the way we're going to do that is by adding to it a dy squared. So this is area moment of inertia. So we're going to take the area and multiply it by the distance, the perpendicular distance between the arbitrary x-axis that we're looking for the moment of inertia about it, and the centroidal x-axis that we've pulled from a table. So if this is the minimum value, we could also back calculate this if we knew the overall moment of inertia by subtracting that out. So that's kind of a cool thing too. There'll be a y component as well. Iy is equal to Iyc plus a dx squared, where we might have some arbitrary axis y, and then our centroidal axis yc, and the distance between these two would be d sub x. Total area, all should be good there. And this is in your FE reference handbook on page 73. All right, so that's what I've got going on there. Now, this is fine and dandy in its own right, and we'll use it, but it's more helpful when we start thinking about composite body theory. Okay, so with the composite body theory, typically it's hard to get shapes to behave around a particular x-axis unless you've done something to push it away. And the way we would do that is by building up a composite body of many shapes, and we can find the moment of inertia for that composite body by going through and finding the sum of all the centroidal x moment of inertias for all the different shapes in our composite body, and adding to it the sum of all those areas times dy squared. And so this is very much like what we did in our composite body theory for centroids, where we might form a table and add up these columns. Iy composite is going to be equal to the sum of the Iyc's plus the sum of a dx squared. So the best way to remember the dx dy relationship is it's the distance between the axes, but there is going to be kind of a subscript mismatch maybe to you as you're remembering that and going through. And so the question becomes, how do I use this to do my procedure? Well, if you want to do that, typically what we'll do is we'll do exactly what like we did for our moment of our centroidal calculations. We'll ID known shapes out of our composite body. And hopefully those shapes show up in our FE reference handbook on pages 74 to 76. Okay. Once we've identified those shapes, we would probably tabulate, make a table of properties. So the question is, well, what properties do we need? Well, it turns out that you can do this. Hopefully this procedure feels familiar because it's very similar to what we did for centroids. And so we'll need our area. And what did we say about areas that were going to be holes? Well, if they're holes, we would have a negative area. We're going to subtract it out. So negative for holes. So we'll need the area. And then we'll need the distance to the centroids. And this is where our notation can get a bit confusing because we talked about this as x and y to the centroid for each shape when we were doing our composite body theory. Now we're using in for centroids. In our parallel axis theorem, this is going to be dy or dx and dy, but it's the same idea, dx and dy. Okay. And then once we have the centroids, we'll need to calculate the first moment. This would let us find the centroid location. So that's going to be XA and YA. Then we'd have the second moment. That's going to be ADX squared and ADY squared. And then we would want to calculate the moment of inertia about the centroids for each shape. So that would be IXC and IYC. And again, we're going to have help from from your FE reference handbook there at the back, 74 to 76. Once we have that, we can sum our components and solve for our centroids using our centroid composite body theory equations from earlier in the semester, and we can solve for the moment of inertia about those x for the composite body around x, y, and xc. But that's going to be around the x and y axis that's arbitrary. If we wanted the moment of inertia for the composite body about its own centroid, we could then back calculate the moment of inertia about the centroid using our parallel axis theorem. So we will have calculated the composite Ix and Iy about an arbitrary moment of inertia, and we will have calculated the perpendicular distances between the arbitrary axis and the centroid, and we'll know the overall area by that point. And so we can actually back calculate the composite centroid, the composite moment of inertia about the centroid, these values, by taking our Ix and Iy and subtracting off the sum of the A, Y bar, and X bar squared. Now, that may be confusing as all get out, which I'm sure it is, which is why we'll work a problem together. Look forward to seeing you in class.